Broadcast is now starting. All attendees are in listen-only mode.
Hello and welcome everyone to our solar storage webinar. I'm Jenny Woodruff from Western Power Distribution, and I'm joined today by Christy Sims of British Solar Renewables, who'll be taking you through the bulk of the presentation today, and Christine Kunik of BRE National Solar Centre, who will be helping with the admin of the webinar itself, managing your questions and also helping to answer questions at the end. So before we start, I'd like to explain how we intend to run the webinar today. To keep extraneous noise to a minimum, we'll be muting the input from the webinar attendees for the majority of the presentation. If you would like to ask a question that relates to what's being presented, please enter your question in the text box for questions that you should be able to see on your screen. Christine will then group similar questions together and will answer these at breakpoints we've scheduled during the presentation. If you have more general questions that don't relate to the particular slides being presented, then you're welcome to use the question facility as well, but we'll come back to those questions at the question and answer session at the end of the presentation. We'll also unmute participants for this Q&A session, so there's an opportunity to have more of a group conversation. So we don't just talk to each other through text at that stage. So the webinar is being recorded, and we intend to make this available from the WPD Innovation website, but I need to confirm that with the manager. We'll certainly make the slides available, definitely guarantee that. And also the final report document on the project that we're actually presenting the conclusions from today is due to go onto our innovation website, if not today, then tomorrow. So the agenda for today is fairly straightforward. We'll start with an overview of the project, as we have a diverse range of attendees today. Not everyone will have seen the previous presentations at the LCNI conferences. And then we'll go through each of the use cases in turn and their conclusions, interspersed with those short question breaks I mentioned before. Then we'll move on to the overall project conclusions before that longer, more chatty Q&A session. And we're hoping to get to that point about 12 o'clock. Oh, sorry, about 20 to 12, so we've got time for the Q&A. So in terms of background then, the project was funded under the Network Innovation Allowance with an overall aim of investigating the potential services that could be provided if battery storage were installed behind the meter at solar sites. The hypothesis was that some of the potential services would benefit the distribution network operator, the DNO, and that if the various services could be scheduled in a complementary way, including potentially providing more than one service at the same time, then this could be a commercially viable proposition for the battery owner. The project had three main phases, which involved procuring, building and connecting the battery, operating and testing the battery, and then finally the sale, removal and relocation of the battery. The procurement reflected our view that a 300 kilowatt size battery was the minimum to see an impact on the network. And we also wanted the battery to have a capacity equivalent to operating at peak power for 2 hours in order to demonstrate some of the use cases that are specific to the DNO. RES were appointed from the four bidders to provide, install and support the battery. They've got lots of experience both in renewables but also in containerised battery operations in the United States. During the operation and testing phase, well, we can divide that probably into two time periods. In the initial phase, it's really characterised by repeatedly finding and fixing teething problems, which meant that the progress against the planned test schedules was erratic. However, the second phase, after the teething issues had been corrected, was characterised by good progress against the test schedule and reliable operation of the battery. Finally, the removal and sale of the battery allowed us to extend the project's learning by trying out a process that's not well established. We think this is the first time a containerised battery has been relocated in the UK. And this has given us new insights into the variety of potential customers that have an interest in owning battery storage and what information they wanted to know before they could decide on whether or not they wanted to bid, and also what they're willing to pay. I'll now hand you over to Christy, who will tell you a little bit more about the battery itself.
Thanks very much, Jenny. I'm Christy Sims. I'm a commercial analyst and engineer at BSR, and I'll just give you a little bit more information about the battery. So we had lithium-ion iron phosphate cells. These are much less thermally volatile than the standard lithium-ion cells and don't have the possibility of thermal runaway, which is obviously great from a safety perspective. The battery, as it was built, could fit into a 20-foot container, but a 40-foot container had significantly less lead time and the cost was similar, so that's why the battery was installed in a much larger container than it was needed to. The 2-hour depth was to help cover off all of the use cases, although it has been noted that the standard commercial depth of a battery throughout this project will be 1 hour. And we initially ran this battery between 20 and 80% state of charge limits, which we then extended to 90 to 10% as we grew more confident with the battery. Contractually, we were allowed to charge and discharge between 1 and 99%, but we put extra limits within Resolve to ensure longevity of the battery. Here is a bit of background about where the battery was installed. So the small yellow highlighted area is the battery compound, and the large blue area is Higher Hill Farm Solar Park. This is a 5 megawatt peak, 4.5 megawatt AC solar park that is totally separate to this project, but it is connected at the same point of connection effectively as the Copley Wood Solar Park. The Copley Wood, highlighted in green there, is a 1.5 meg peak, 0.99 megawatt AC park. And the fit on this smaller park is measured at the inverters, so the subsidy from installing this battery was unaffected. This shows the single line diagram to demonstrate how the battery is connected to the network. So you've got the bus bar of Millfield primary substation on the left there, and then the blue 11 kV feeder running to High Hill PV generator. And then the Copley Wood PV farm was connected into the spare ring main on the DNO side. And then on the private network side, the Copley Wood battery was connected behind the meter on a spare ring main unit there. And then both of them had power quality meters installed so that they could be metered separately. This project was designed to investigate 9 different use cases in total, which I'll very quickly run through. So we start off with arbitrage, which is the sort of easiest use case to understand. You try and buy power cheaply and export it at a higher price. Peak demand limiting. This is network support. So you try and reduce the max annual peak seen by the network and avoid reinforcement. This was expected to be useful in areas going forward which have slowly increasing demand, and then it would help equipment stay within their limits. Local demand peak lopping is very similar to peak demand limiting, in that it allows expansion of load in constrained areas without reinforcement, although this would be a sort of direct contract with a factory or company that wanted to increase its consumption but wasn't able to due to network limits. Low demand grid voltage support was involved increasing loads overnight to help reduce the voltage. So in rural areas where the voltage rises very high on feeders that aren't loaded overnight, we add additional load from the battery, and it was expected this would dovetail with arbitrage and take advantage of lower overnight prices. And the final 5, voltage control by reactive power. So another way to control voltage is by adjusting the power factor between leading and lagging, and therefore the voltage can be controlled like that. High voltage is a problem in many areas due to the increased amount of distributed generation and sometimes the overnight underutilized assets. So this was also expected to help. PV export limiting was the case that everyone immediately thinks of when you combine a solar park with a battery. So you import power during the middle of the day, potentially when there's a grid constraint, and so you allow oversized parks on smaller grid connections, and then they export in the evening where the solar park is no longer using its export allowance. Variable PV export limiting. This is to demonstrate that you don't have to just set the battery at a particular level, you can change it day by day, So if there were different network conditions, let's say something was being repaired or replaced, you could artificially lower the export limit for a time and still make use of some of your PV power. Realistically, within this testing, those were tested at the same time because every export limit that I placed was a variable one because I could set it manually. Ramp rate control was looking to investigate how to improve power quality on the grids that solar parks are connected to, because the fast ramping of solar can cause voltage fluctuation. And the final use case was multiple battery systems. There was initial fear back when this project was first discussed. This was back in 2013 and 14 that this project originally was being discussed. There was a fear of multiple batteries being contracted to do the same thing in the same area, relying on their local sensors, and then if one battery triggers slightly earlier, the second battery wouldn't trigger at all because the issue appeared to have been solved. We weren't able to test this because we only had the one energy storage asset, but the market has sort of moved on and evolved, and it seems very likely that any sort of grid services will be controlled from a central point rather than reliant on separate sensors. So it's not really considered an issue anyway. We then had to come up with a base case scenario to be able to compare all of these other use cases against, because it's all very well saying one earns more money than another, but does it earn enough to make the project viable? So base case, the relevance of this base case has actually faded very recently due to frequency response contracts declining. It's very difficult now to get a fast frequency response contract due to the oversupply. But if we look at 2016 versus 2018, we can see that the revenues declined by 62% in 2 years. Now, energy storage costs have also declined, but only about 40%. So the revenue decline has outstripped this. And no frequency response contracts available mean this revenue dips further. But this was at the time the baseline standard commercial case that we were comparing everything against. Arbitrage, as I said earlier, is the sort of simplest concept of how to make money with a battery. Now, we assumed initially that the intraday price variability would be enough to generate a profit every day, even with simple timed imports and exports. However, the existing PPA agreements on the solar park meant this was impossible. The solar park is a flat import day-night summer-winter tariff and an N2EX export tariff. Now, standalone batteries wouldn't have this issue because they would be able to negotiate their own agreements and aim for more variability. So I believe that this is a prime candidate for being passed over to an external energy trading floor who are dedicated to finding the peaks and troughs in prices and making money out of them. The fact that this scenario is location agnostic means that it's likely to be the new base case revenue stream for storage now that frequency response has declined so much. This graph is quite busy, I know, but it shows the pricing differences of the agreements and markets for Copley Wood. So the summer and winter days are right at the top there, the red and purple lines, and then the green line is the overnight import. Sorry. So those are the three price levels we can import power from the grid to the battery at. And then the orange highlighted area is the N2EX next day auction, the PPA for the site. You can see why a solar farm would choose this over the standard system buy price because it's significantly less variable, and solar asset owners are always looking to remove variability from their revenue streams. But you can also see that at nearly every point, that export is below the cheapest import that we can get, and certainly below the daytime import. So that really reduced our ability to do real arbitrage. However, we wanted to investigate if it would be profitable for a grid-connected battery to do it. So we created a virtual PPA, including everything we expected would be included and excluding certain things that the market said it was going to exclude from charging energy storage. And in that way, we were able to do a simulation of how the battery would have performed over 2017. This shows the average N2EX export day for 2017. and it highlights two key areas to target for arbitrage. That's import at 5 p.m. and export at 9:30, and then import at 3 p.m. and export at 6. So these are the results of the virtual PPA ran for 2017. So the simulation was idealized. So it looks at the export price for a half an hour and compares it to the previous 48 half hours. If the trade was profitable after a round trip loss, it would trade. Then those two times are locked off and the next calculation is run. And this way would stop half hours being double counted. The opportunity cost of bidding out of the FFR market just for the time it took to do that particular trade was taken into account. So you can see in 2018 that reduced the profit down to about 5,300. And in 2016, with those much higher FFR and capacity market prices, it barely reaches £2,000. And this was very idealised. As I say, it was based on the ability to bid in and out of the FFR market on a half-hourly basis. Currently, you have to do that a month ahead. And if we look at the table of revenue able to generate for a month of arbitrage versus a month of even the low FFR rate of 2018, you can see that there is no month where arbitrage is more profitable than FFR. This is assuming 24/7 FFR contracts. So the revenue available from arbitrage is 1/3 that of frequency response. The other thing about arbitrage is it gives a varying amount of income per month, and so it's less predictable, and that is worse for investment cases. So some conclusions from arbitrage. The existing grid agreements of solar parks are very much the enemy of arbitrage. The solar park wants long-term certainty and reliability, and the battery really wants access to volatility to be able to make money. The increasing penetration of renewables is likely to increase volatility, but gas peaking plants, diesel, etc. will cannibalize this because every generator is chasing those high prices. Dedicated teams are required for the energy trading. It's not something that each individual asset owner should be trying to undertake themselves because they won't be able to do it as well as the big houses, in my opinion. The big advantage of this is that there's no special contracts required. You don't have to try and bid against other people to get an arbitrage contract. Grid costs do make a big difference on profitability, and there is a lack of visibility ahead of application and installation of what exact grid charges you will be receiving. So it's hard to pick ideal locations, but the base case of arbitrage can work at any location. That brings us on to our first question and answer session. For any questions that have come through?
No questions have come through yet.
Oh, no questions. Okay. Just
give everyone a few minutes to either raise a hand so I can unmute you to ask a question in person, or if you want to type it in the questions area, and then I'll relay that to Christy and Jenny to answer.
Okay, and just like to check that everyone can hear us as well, probably. That's always a good.
Okay, we've got our first question from Mike Garwood, who's asked, what is the cost of the battery system? What's the cost of the battery system?
So we don't have a cost for the battery on its own because the contract covered that, plus also installation and support. And I believe that was around the 650 odd thousand mark. So
that's what I recall to be as well. Yeah. Yeah.
Okay. And James King has asked, I'm assuming specifically on the business cases we've been looking at so far, how long will the battery take to break even?
Well, I'm not sure it would under this scenario. Certainly with the costs, the high costs that we initially started with, I mean 8,000 a year versus 650,000. It's not going to pay back in its operational life.
No, I think we were anticipating battery costs falling lower. Certainly at the time that we looked at this project, battery costs have been falling quite significantly.
Yeah.
And I think we were anticipating them continuing on that downward trajectory to the point that would help the business case as well.
Yeah, they've battery prices have begun to plateau because quite a lot of the manufacturing is now reaching maturity levels. They accelerated their and took advantage of other industries' manufacturing techniques to be able to speed it up and reduce that price decline. But they're not declining as heavily as they were before.
I think maybe the electric vehicle market is coming on stream a little bit faster than we anticipated as well.
There's I've heard some various manufacturers stating the majority of their capacity is now going towards EVs. So grid-connected batteries could be in competition with that.
So we've had a few more questions come in. Mike Everest has asked, would short-term predictions of solar radiance and hence site power improve the revenue generation?
Well, solar. So the solar peak lopping is a slightly separate use case we'll come to later. This was looking purely at grid-based arbitrage. I would say that behind the meter batteries, if they do not renegotiate the power purchase agreements of import and export solar parks, can't do arbitrage, because in some cases, I mean, we had a fairly variable PPA there, the N2EX, because that meant that the solar park was available for other opportunities as they came along. Some solar parks are entered into multi-year flat rate export amounts, or just rising with inflation. And then there is literally no opportunity for capturing a higher price at a different time with those. We'll come on to sort of solar peak lopping and trying to increase the revenue in a bit.
I'll leave Mike's question there for a bit. So some of the others are referring to bits that we haven't quite got to, but however, Giorgio Cristo has asked, what is the power electronic converter type that is used for the connecting to the grid? Any ideas?
I don't. I would have to look that up. I don't think that's
I'm afraid
something I have to handle. I'm afraid.
We'll flag that one and come back to you, Giorgio, on that. And I think
to come back to Mike's question about forecasting solar output. Not as part of this project, but as part of other projects. I'm certainly interested in improving our ability to forecast solar output because we're looking to understand what we require from flexibility services and to dispatch flexibility services. So we're actually looking at forecasting generation output as part of our EFS project.
Okay.
That's something that we're looking at the moment, and I know it's typically been an area that's been very difficult to do. So even though it's of less of commercial interest to solar farm operators to a large extent, we're certainly interested in. If you've got great ideas for how to improve solar forecasting, we would be interested in finding out what they were.
Well, I happen to know that Mike has just finished an Innovate UK project.
Okay.
So I'll put you guys in touch.
Maybe email me after.
Excellent. Okay. Well, I think some of the other questions actually will be answered a little bit later on in the next bits of the presentation. So, Chris, if you want to carry on, feel free to keep sending questions in, guys, and there'll be a break after the next section to ask some more.
Yeah. Okay. Next use case is network demand peak lopping. So this shows the average UK load over 2017, taken from national grid level data. And there is a clear standard peak, as you might expect, between 5 and 8 p.m. there. And a 2-hour peak lopping is not good enough to take 3.5% off of this. So you would need 3 hours for that. If you were able to have 3-hour network support, you could shave 1 gigawatt of generation on average across the UK, which is quite a significant target. And by avoiding this peak, things like the maintenance window on DNO and even higher up grid assets can be extended, because they'll be able to extend that summer window where they're working with lower loads, because the network wouldn't see that amount of load. This is a brief look at the requirements that are on DNOs to restore power in the event of an outage, and why there's so much redundancy that needs to be available in the grid. So you can see if there's over 60 megawatts of load in an area, then within 60 seconds, 2/3 of that needs to be able to be brought back online. And with the fast response that batteries are able to offer, this would be helpful towards management of the grid, and then help avoid the standard, bigger cables, bigger transformers that traditionally have been used. Part of the issue of this, though, of trying to avoid this reinforcement, is local networks don't follow national peak loads. So what drives that big peak in the evening is domestic dwellings, because businesses often shut down 5 o'clock, 5:30. Everyone goes home, starts cooking and eating, etc. And the primary substation load characteristics depend heavily on what mix of loads they have connected. So if it's a mainly industrial area, actually there won't be the evening peak that you'd be expecting. It would actually decline, whereas a heavily residential area would have a much bigger peak during the evening. If you can have a predictable peak like you get with a domestic substation, then you only have to have the battery contracted for less hours. And the way that I've analysed this is that there will be a base case for a battery that it would operate in normally, and that would be the investment case, and then it would effectively bid out of whatever it was doing to offer extra network services depending on the prices offered. So the less hours that the battery is needed to be dedicated to this, the cheaper the contract is. This sort of peak locking is only useful where load is close to the maximum peak rating of assets already, and it has to be coupled with slow predicted growth, because otherwise there would only be a year's worth of peak locking, and then there will be reinforcement being done anyway. So we set the battery up to continue exporting until 8 PM approximately here, and I've overlain. We have Argand monitoring installed at the primary substation, which allows us to monitor the generational load on the 11K feeder that goes to our site. And you can see the battery supporting the power levels through the end of the day. And then when it stops there at around 8 o'clock, the direction of power reverses, because the standby load of the Copleywood and Higher Hill solar farms means that power needs to go back towards them. So you can see here, exporting the power at the park site does have a direct impact at the other end of the feeder on the primary. We're trying to analyse primary's load profile, and there's a slight issue. This is taken from WPD's analog, so their internal data monitoring system. And you can actually see that you find out that we've got generation data from one of 3 solar parks that are connected. So there are 2 5-megawatt parks. The 2 5-megawatt parks are the same design as each other, so Higher Hill Farm and Butley. And then there's the little Copleywood Park that we have the detailed generation data for. So the assumption was made that the Higher Hill Farm would be outputting a similar percentage of generation as the Copleywood Park, because they're in the same location, and with the other one being less than 2 kilometres away, just extrapolated that would also be acting in the same way. And in this way we could try and estimate how much generation was actually being pushed into the primary. So the blue line is the raw WPD analogs. That is what they see on their system as load during the summer day. And then the red line is our calculated generation, and thus the green line is actually what we're expecting the consumption from Millfield to be. So you're getting a very big morning peak there. Now there's quite a few large peaks and troughs that are very sudden, and I suspect that's an artifact of trying to extrapolate 3 parks worth of data from one, so you can smooth those out. And I believe that the large morning peak there could be from the very large school that's attached to primary. And thus, when they're starting up at the beginning of the day, they have much larger loads. It demonstrates that it's quite difficult for a DNO to actually find out what load is being put on their system, because they don't have visibility of the generation. Looking at trying to peak lock took 2 years, 2016 to 2018, and found the maximum half-hour load at any point over that 2-year period. So this is showing the maximum load that there has been in 2 years on those primaries. And what we find is that there is an absolute peak at 5 p.m. within the red period. So that the actual peak does follow the national expectation. And all peaks over 16 megawatts, if we took 16 as our arbitrary limit we wanted to use the battery to reduce, for instance, they all occur within the winter months, meaning you wouldn't need a network support contract year round. You'd only need it for the 3 winter months. If not all of the battery power was needed, then this would reduce the cost of the service even further. Although quite how that would work and whether the battery would be able to use the rest of its capacity to import would have to be negotiated with the DNO. Looking at the potential profitability of doing this, there is a time value of money. So by delaying upgrades, you save money. Firm capacity requires replacement of 2 transformers. So we tried to calculate the saving of delaying this reinforcement. And it's been assumed that 20% of this saving would be retained by the DNO, going towards admin costs of dealing with the contract, and batteries potentially having slightly more downtime than a transformer, that kind of thing. However, the longer contract length, in this case, means that lower prices than the absolute savings we calculated here might be acceptable for the battery, because the overall energy storage industry is really wanting longer, more reliable revenue streams going forward, which is why the capacity market, even after it declined so much, was still fiercely competitive recently. We've then got the local demand peak lopping. This is the only system that responded to an external signal rather than just relying on pre-timed schedules. So here you can see that we've got a standard export level, the 100 kilowatts, as if we're supporting the network between 5 and 7. And then if the battery receives an external signal, like an active network management signal, a soft intertrip, the battery increases its export, and then once the signal is removed, it decreases. Exactly how that would work, or whether there would want to be a timed delay after the signal was removed, could be negotiated individually. But what this demonstrates is that the battery can operate with other external systems. And this could eventually end up being a sort of DNO offering. If the DNO knew a battery was open to being contracted in this way, and the DNO was only able to offer a new connection with reinforcement, they could say, well, you could go and speak to this asset owner and try and negotiate a system like this. So this is the first combination of 2 methods as well. We're operating 2 things at the same time, the standard network support and the external signal received. It would also work, as I say, with other use cases, depending on what the exact limits were on what the battery could do while it was providing this additional support. It does require specific network uses, conditions to be useful. So the system has to be close to capacity and someone wants to have an increase in load. And that's when this use case can come into its own. The fact that we only used a partial capacity of the system, 100 kilowatts, meant the opportunity cost was approximately a third. And that means the opportunity cost is very low, £436 per 100 kilowatts for 2 hours support every day for 3 months. And this again demonstrates the time value of money by saving the reinforcement cost. So a 10-year delay of £115,000 cost apportionment factor payment would allow a contract of 750 kilowatts of power for 2 hours over 3 months. Again, assuming against the FFR case of being able to get a contract. It doesn't work out well for network sections with unexpected and unpredictable loads, because then you have to contract for a longer time and the opportunity cost goes up. But this use case isn't always about absolute cost versus the cost of reinforcement. Sometimes there's quite a large delay on when DNOs are able to schedule the reinforcement, and waiting 2 to 3 years for a connection to be upgraded could be damaging for a business falling behind its rivals. looking at these two use cases in the wider market, things are beginning to happen. SSE is looking to meet its N-2 obligations at 132 kV using constraint management zones, offering energy storage or gas or diesel peaking plants. The batteries couldn't do the 5-hour requirements for this service economically by themselves, but they do have the fast response that then could be the front end to other longer term generation. And some DNOs expect to have many contracts with different assets to get the desired result out of the system. And WPD is also beginning flexible power to try and stimulate the flexibility market, speaking to people who have assets already. So, any questions about those two use cases?
Right, well, whilst we wait for some more questions to come in, I've had two general questions about the project.
Thank you.
One from Andrew McKenna, asking you to go into more detail on the life of the battery after the trial, including the process for sale and disposal. Now, I know we've got sale and disposal coming up,
Yeah.
but just the life of the battery. We've got another question as well from Ed Hill, who says, how many cycles did the battery achieve each year during the trial?
I mean, in total, it did approximately 400.
Yeah.
I'm just remembering this. I actually wrote the degradation part of the report quite a while back when I did the testing, so it had, in some ways, the cycles is not a true reflection of what the battery did, because it did about 400. You could say that's 1 year of frequency response. But there's a time element to batteries. They do degrade by themselves, and we were doing often 20 to 80, 10 to 90% cycles, which are significantly more damaging than frequency response cycles, which often have it hovering around 50%. So the deeper and higher you charge a battery, the quicker it degrades. And this battery, towards the end of its life, the cycles are actually clustered towards the end of the testing, when we got everything run in and all the software set up as we wanted it. And it was doing 1.5 to 2 cycles a day, depending on solar conditions and what other triggers it was responding to, which is a very heavy use for a battery.
So do we think there was an impact on, because of the innovation trial, on the actual lifespan of the battery compared to how it potentially could have normally, if it was in a normal routine?
I mean, we had degradation of approximately 7%. It's detailed in the report exactly what the figure is, but it's approximately 7% over the 2 years. It's difficult to compare that to almost anything else. People are very guarded over degradation, and there's not that many batteries actually out there that have been working for 2 years yet. So it's really quite hard to compare it to other lithium technologies. I would say that is higher than the predictions I've expected from frequency response. We're using this for very different things. Realistically, the key is what can you get a guarantee for when you procure a battery? Because if you can get a guarantee that says you can do this number of cycles and they can be full to flat cycles rather than frequency response cycles, then it sort of no longer becomes your concern. You're able to offer all these services, but the market's still in an early stage. We're not seeing the explosion and the data of degradation that we'd quite like to see. The battery was still above, it was oversized initially. So the nameplate capacity, it's still above its nameplate capacity now, after 2 years of work, because it was over 700 kilowatt hours when it started its life. So in terms of the asset as it is, it's working very well, and it's maintaining its round trip efficiency. But, yeah.
Excellent. Okay, well, we have got some other questions, but they're more around other areas that we can cover in a minute.
Okay.
One more actually from Giorgio about the location of the PV installation. Is it selected based on the optimal power transmission or based on the maximum power generation?
I don't quite. Sorry.
I would say the location of the installation wasn't chosen for either of those reasons.
No, the reason that the PV installation was a separate commercial concern that existed before the project. I think it was envisaged to exist before the project. It's a standalone operation, and is a commercial. That's why the PPAs weren't renegotiated. It's because the solar park is a commercial entity that couldn't afford to lose out on that revenue. It was selected because it was wholly owned by BSR, and we were working with WPD for the trial, so we could then connect it and have freedom to do what we liked with it. And, for instance, shut down the park for half a day to install the battery. If it was an external owner's park, there would be a significant pushback on that. I think it's fair to say.
Excellent. Okay. Well, we'll save the remainder of questions for one of the other sections.
Okay.
Thank you, Kristen.
Right. Our next use case is raising minimum demand or reducing voltage rise. And you've got those the wrong way around. Simple use case. You just import the power overnight to increase the minimum demand and reduce the voltage rise. So again, we wanted our GAN's information on this. That's why we had the monitoring installed, because we thought, well, we could see a significant change of voltage at the POC, but by the time it runs down the kilometres of 11 kV feeder, it might not have any real impact back at the primary. We did have a bit of an interesting time with the local power quality meter for the battery. It showed imbalances of 500 volts across the 3 phases, which was obviously concerning when we first noticed it. However, the PQM for the solar park, which is connected in an almost identical location, showed pretty much identical voltage across all 3 phases. So it was put down to a configuration or zero error. And because it didn't directly impact any operation of the battery, it then wasn't investigated, because it would have delayed further testing. We were looking for actual changes to the voltage, and of course the battery could only work at maximum capacity for 2 hours, so we couldn't do a whole overnight import and see what the difference was. So we ran the tests over several nights. This is showing several nights worth of tests. We're looking for any obvious dips when the battery is importing. Now, the first night on the left looks quite promising, and then the second night, as we start importing, the voltage shoots up and then seems to sort of go back down again just before we finish importing. I've boosted the voltage at Millfield by 150 to match the POC voltage, because there is a voltage drop across that feeder. And this way they can be directly compared. The changes in voltage can be directly compared. As it will be seen during peak lopping, the voltage at Millfield seems to be driven by the solar, and overnight Millfield voltage is variable, so the voltage is driven from the substation. We believe we need a larger load to actually see any impact, because we didn't see one here. Admittedly, the visibility of this use case is not helped by the fact we are on a live network, which in some ways is the point, but there's a tap changer that is independently deciding when to change over at the substation. We don't have visibility of that. There's a constantly changing amount of loads, and we don't have second-by-second monitoring at Millfield. It was every 10 minutes was the closest we could get. Well, I think it was every half hour, actually. Every half hour was the closest we could get. We also didn't really see any synergy with arbitrage. It's not necessarily always going to be cheap prices at the time when there's minimum demand on the local network. So, looking into why we're not seeing the effect that we wanted, the overnight load on Millfield Primary barely dips below 5 megawatts throughout the year. So on the most lightly loaded day of the year, overnight, you've got 5 megawatts of load going through those transformers. So the battery can add 6.2%, which is not enough to make any reasonable difference to the overall voltage of the network. Now we come on to the more complex reactive power control. So briefly, active power is the power that does work, and reactive power is just essential to the network. It's caused by transformers and capacitors on the network. And ideally, you try and keep the power factor, the ratio of active to reactive. You want as much active as you can and the absolute minimum of reactive power, because that's the most efficient way to use your assets. We can see here a section, actually I'll just briefly go back there. That graph on the bottom right shows the active power P versus the reactive power Q of the inverters. So they had a perfectly circular PQ curve. They're able to operate anywhere inside that circle, which means there doesn't have to be any active power flow at all from the battery to be able to import or export reactive power. Now, the interesting thing is that unlike every other use case, if you want to offer 100 kilowatts of network support, you have to take 100 kilowatts away from your base case. But with reactive power, due to operating on this curve, the inverters can actually do two things at once. So by giving up 17 kilowatts of active power, you can offer 100 kVAR of reactive power support. So that non-linear trade-off means a slight derating of an asset can start helping a network either adjust its voltage or potentially improve its power factor if there's other influences at play that cause it to be lower. So this shows an opportunity for multiple assets working together, each giving up a tiny amount of their capacity to be able to support the network, and thus the opportunity cost is very low, and therefore the opportunity to help is greater. However, we took several overnights of untested days. I'll try that again. We took several nights worth of data from nights when we weren't testing, and we were looking for a pattern. So I set the voltage. It reads artificially high, 11.6, 11.7. That's due to the PQM reading error. That's not actually what the battery was trying to achieve, but we're looking for a pattern that follows the red line that demonstrates the target voltage. So we're looking for changes from the standard overnights to the test nights. And we were able to have a very small influence on the changes in the average voltage. So overnight, usually it was around 11.66. So when we set it to 11.6, we were able to reduce the voltage slightly. When we set it to 11.7, we were able to raise it slightly. And so the change in the average voltage, we're seeing a pattern there of some effectiveness. But we're not seeing such a clear pattern in any of the other graphs. And the control data, again, is noisy as it's taken from the live network. But the battery, at this point, when I set it to 11.7, it was working at full capacity to try and influence. It was giving it full 310 kVAR, and we're still not seeing a very large effect. I've reported some of this back to WPD throughout the process, and independently they've been doing some other tests on reactive power, and they found that a 400 kVAR StatCom wasn't really having an impact at 11 kV. So the fact that our smaller battery wasn't having an obvious impact was not particularly surprising. Positives to take from this use case is that the control algorithm worked flawlessly. It gave proportional responses to changes in voltage, which I've demonstrated with that graph below there. You can see that there's mirror lines either side of that 11.6 kV volt line there in green. And the fact that you're able to do this non-linear trade-off means that even if it's a smaller asset, if you combine several of them in an area that requires support, it starts having an impact. And indeed, some other research events in UKPN, for instance, their flexible power, not flexible power, power potential, is looking at this kind of thing, using multiple assets working together to have the desired impact. Is there any questions about those two?
So if everyone wants to send in any questions they have, particularly over those use cases. We've got another general question from Neil Bailey, asking whether or not you'll be showing the basic financial model for the project, so we can see IRRs and other financial metrics. Is that in the final report?
There isn't really a financial model as such, other than the analysis for each of the use cases.
Because I mean, so much of it depends on location and what else the battery can do, that it's very difficult to try and make, here's a model, here's the IRRs, away you go, because all of the DNO use cases, for instance, compare directly what else could they do within their network to be able to have this effect, what's the cost of that, and it's so there isn't an IRR, because first of all you have to generate a model for overall energy storage investment, and what's the IRR for that, and that means finding current prices from various manufacturers, grid connection costs. All of these things have a huge impact on what IRR you can achieve. So what we've done is we've taken the base case commercial model, which during this project was what people were investing in and expecting to build batteries and building quite a big pipeline across the UK on. And then we compare, if this is the base case, you have to pay that much to get people to do anything else, because otherwise why wouldn't they just carry on as they are? And in that way we can compare it. So I would say this research is meant to go alongside an investment case, because a lot of these, other than arbitrage, I would say, are additionality rather than dedicated revenue streams.
Okay. Neil's actually just clarified, saying he actually meant it for this particular project. Have we done a financial analysis of this particular project?
No, we haven't.
No, I think though you can infer that it doesn't work. That it only really worked for this particular project because it was NIA investment. Because at the end of the project, they were quite happy to have the battery relocated rather than for it to remain on site. There wasn't going to be enough income from the solar peak lock-in and the other local services to make that worthwhile.
And the testing did cost money. I'll point out that it cost money to have the battery there. Even just the standalone standby import runs into 4 figures each year, and then because they're sort of the king of grid assets, if you like, they're very expensive. They can do anything. You need the battery to be working flat out at all times, doing something that generates money. And we had the battery sitting idly there, and as I say, quite a lot of the time it did cost us money just to run the test. Now that doesn't mean it would cost money if you were making a commercial one, because you renegotiate certain agreements and that kind of thing. But yeah, it was it wasn't worthwhile keeping the battery there.
Okay, I've got a question from Alex Gator, which is, what is the average O&M contract cost per megawatt on a grid-scale battery system that is used in front of the meter for FFR contracts? Pluck a figure out the air. We didn't factor in O&M contracts into this particular.
The operation and maintenance cost was part of the package cost for the contract with RES, so we don't have a breakdown of those elements within the cost.
If you would like a quote, BSR O&M team would be happy to speak to you.
Nice.
But yeah.
Okay. Last question for this bit before we carry on. So Gordon Brown has asked, surely most solar farms are located in areas that are less likely to be in constrained areas of the network. To what extent do you think the results of some of the use cases which you've shared with us thus far would improve if the location and connection type have been selected with those use cases in mind?
I mean, it's true that solar parks were initially put in areas with less constraint because rural networks often had spare capacity, and you tried to connect wherever was cheapest, which is the place with capacity. I wouldn't necessarily say that's true anymore. There's huge grid constraints on huge stretches of the network in rural areas as they try and absorb the generation or deal with the demand and the swings between the two. And there's a lot less assets in rural areas, grid assets, to help stabilize these effects. So in some ways, the centralized system, even though it's running more at its peak in urban areas, could be more resilient to voltage changes, for instance. Whereas these long overhead lines are less so. So these services might be a better way of stabilizing that than, for instance, making a thicker 11 kV 7 kilometer feeder, because the voltage is starting to fluctuate at some points of the year outside of statutory volts.
I think certainly if you were connecting a solar farm under active network management, you would have an appreciation of how many half hours in the year you might expect to be constrained, and that would give you a little bit more information to do your own sort of solar peak lopping type use case. You would then be able to see what that would mean for the battery. But of course, we can't predict with complete accuracy exactly which half hours those would be. But it might be that installing a battery on the side that's constrained makes more sense and gives you your fundamental use case that you can then build upon. It's also likely, if it's an AN connection, that it may be able to provide services to neighbouring customers as well.
I'll also say, if you're wondering about the other use cases that are sort of grid support, those have sort of been analysed in two ways, and not just as a solar connected battery. We've also looked at this as if it's just a battery that was connected to the grid and therefore could be connected anywhere. Because to sort of pigeonhole this as a solar connected battery, so we have to look at only things it could do if it was connected via solar. For instance, the arbitrage simulation I ran was 24 hours a day arbitrage. Now, the battery, as it wasn't able to export if the solar farm was exporting, because they shared that capacity. There was only 1 megawatt of export. So if the park is going flat out, the battery is not allowed to export. So I wouldn't say this is location specific, or necessarily some of this specific to being a solar attached battery. We've tried to get as much learning as we can out of the asset.
Cool. Okay. Over to you for the next section.
Okay, this next one is about being a solar attached battery, because it's solar peak lopping and glass ceiling. So hard to do this on a standalone system. I've tried to separate this into two different types, voluntary and involuntary. So voluntary, all of the peak lopping at Copley was voluntary because we didn't have a constrained grid connection. So if we hadn't imported the power into the battery, it would have flowed out onto the grid and got whatever price it was being sold for at that point. Involuntary is using power that would otherwise be constrained. So let's say the inverters are software locked to a lower level. You could have a system that, when the battery is empty, unlocks those inverters, and the battery maintains an export, the standard export level, and it charges itself up. And then once it's full, it relocks the inverters to a low level. So there's different amounts of revenue going to be generated from each one. But to give you an idea of why this could be helpful, if you look at the graph on the right, this is Hawaii, and there's a thing called a duck curve, which shows the push down of power prices in the summer in the UK from solar. And in Hawaii, they've got a huge amount of solar, and so they have something called the Nessie curve, which is a much steeper, much sharper curve. So they're getting backfeed. In 2013, they got backfeed at 46 kV level, so pretty high up in the network. And then they're often running sort of oil generators, I believe. So they have to go from that tiny amount of load, in that case 1 megawatt for the standard blue 2013 line, back up to 5. And they have to do that in a very short time and run all their generators flat out to get them ramped back up. So on that island, the power price arbitrage between midday and 5 p.m. will be very large. This is demonstrating the battery in peak lopping mode. We set the peak lop at 450, which is the orange line, 450 kilowatts. The orange line running from left to right there. And then the purple is the generation of the solar. So every time the purple goes over the line, the red line, which is the overall site output seen by the grid, should stay at 450 kilowatts. I would say that the battery works at this fairly well. There is some excursions both above and below the line. Some of these are not the fault of the battery. So if you're looking towards the right-hand side of the day there, actually the generation was more than 310 kilowatts above the peak lopping limit we'd set. So the battery ran out of power capacity to be able to absorb that. I would say that moving forwards, the algorithm needs to be optimized, but it wasn't specified to comply with G100 export requirements because there was no export limit on this site. So I think as an early example of peak lopping, it demonstrates it's working quite well. Going forwards, as I say, batteries respond in less than half a second to frequency response information, so it shouldn't be an issue to make it respond to the solar within the required 5 seconds. So this graph shows how much energy storage would have been needed to peak lop at 80% of the overall power in 2017. Selected 80% because 20% oversizing was deemed to be the smallest oversizing a developer would have the extra expense of looking at a battery rather than just software locking inverters, because quite a lot of solar parks just have a very high DC to AC ratio and they don't have any batteries to try and take advantage of any of that. So on the sunniest days, you would need 1.2 megawatt hour of storage to be able to capture all generation and constrain the output to 800 kilowatts. However, a 620 kilowatt hour battery is able to capture over 80% of all that energy. So doubling it to 1.2 would be a significant waste of money. You wouldn't be able to get the use out of the battery. The opportunity cost for this is very, very high, because the battery has to be available between sunrise and sunset every day for any time that the solar park is likely to go over 800 kilowatts. And you can't even take average irradiance figures for the next day to be able to say, well, we won't need the battery tomorrow, because there could be peaks of irradiance and then troughs, unless you therefore take the hit that the battery won't be available and you'll have to constrain what those excursions would be. So there was 2 types of peak lopping, and I again ran a simulation after doing some real tests. So the average price increase from 2 to 4 p.m. and 6 to 8 p.m. is £17 per megawatt hour. So you get quite a reasonable uplift from shifting the power that would have been exported then and exporting it at the later point. So the system was set to export as much power as possible, solar power, not importing, between 2 and 4 p.m. and export it again between 6 and 8. And this would have generated revenues of £2,750 over the year, so we're not talking about huge amounts of money. And the base case opportunity cost is £6,100, so that's the battery being unavailable for 6 hours a day. That's a simplistic time-scheduled system. We also looked at an advanced solar peak lopping. So I decided to, this is again looking at idealized incomes. So if there wasn't enough solar generation between 2 and 4 p.m, then the day was rerun, the simulation was rerun for that day with an extended import window going half an hour back each time. And this generated revenues of £3,800. We used real generation data from the Copley Wood Park to be able to do this as well. So the whole of 2017, all of the second-by-second data for that park was used to do this. This gave a 55% increase in cycling for a 38% increase in income. And again, it's difficult to say whether that's worth it. I mean, my instinct is that it's not, but it depends what guarantees you're able to get. The other thing is that the opportunity cost is very, very high, because you would have to be available to do peak lopping for a large proportion of the day if there's poor generation days, but just enough solar to be dribbling in throughout the day, and then you export it at that higher price. Again, the income from this will increase if there's a greater penetration of renewables and therefore more volatility. Final use case, output smoothing, ramp rate control. So we found that the voltage does fluctuate in line with solar production. Again, we're assuming that the PV production from Higher Hill is likely to be very similar in terms of percentage that it was at Copley Woods, because they're literally in the same place. So you can see here the POC voltage versus the solar output, they correlate very closely. The bigger gap on the left and just off the edge on the right there, we believe is the tap changer changing at Millfield at the end of the day when the generation drops away. So that's why there's a big gap there. But most of the time it's following very, very closely. These voltage fluctuations reduce power quality, and ramp rate control can reduce these fluctuations and reduce tap changer engaging, and therefore reduce the cost of maintenance of those. So here we have ramp rate control. And you can see the orange being the solar generation. There's large dips in generation at a variety of points, and yet the output level of the park is maintained fairly well, specifically towards the middle of the day there, where the output is maintained as an average of peaks and troughs of the park. The larger troughs, again, the battery was too small to be able to fill in entirely. This is due to the sizing of the battery rather than an actual problem with the control system. But we're still getting grid voltage fluctuation, even though we're reducing these dips by 50% at least. Why? Well, it's High Hill again. Although we're 31% of this park's rating, we only work out to being 6.2% of the overall power flowing from the site. So it's too small to have an impact. But again, we have proved that the battery can fulfill this use case and is working reliably. This is another noisy graph, but what we're showing here is that the POC voltage and the Millfield sub voltage follow very similar patterns overnight, but that during the day the POC is significantly higher than the Millfield substation voltage when there's generation. So the green line is generation, and then you can see a large gap opening between the orange and blue lines there. So there's a large voltage drop over the feeder. And this shows that actually the ramp rate control would be best utilised at the POC rather than at the primary, because the POC is the place that's most likely to go outside of statutory volts and have the biggest swings, whereas the network itself at other parts can absorb it. Ramp rate control, however, doesn't have to cost nearly as much as the other use cases, because you need a very short duration battery to be able to offer this particular service. It needs to have high power, 80 to 100% of park rating, because you can get 80% drops in irradiation on cloudy days. It could even be linked into DC strings to reduce costs, because it's just moderating the export. And a 5-minute ramp rate can be provided by only 5 minutes of energy storage that's waiting at 50% to be able to offset whether it's an increase or decrease. 5 minutes is significantly longer than tap changes take to respond, so much tighter control of the voltage on these networks could be maintained. And that graph on the right there is demonstrating how even a 100% solar power drop, you can reduce it to a gradual decline over 5 minutes, just with 5 minutes of energy storage at 50% there. If you did want to connect it directly to a primary, you could allow aggregation of multiple generators and loads and try and improve the overall voltage quality at the primary. So you would then monitor the primary load instead, and if the load suddenly dropped, you would increase, and if the load increased, you would drop to try and smooth out any voltage changes there. And you could do that more quickly than a tap changer could. It looks like this could be an opportunity for supercapacitors rather than the traditional lithium, which would suffer greatly at this kind of power. And back to questions.
Okay, so that was the end of the... There's a use cases. Yeah, right, yeah. Okay, so I just got a couple of questions still outstanding, which I'll ask unless any more come in. So we've got one from Giorgio. In a contingency situation, what are the effects of the battery bank? Is the battery bank going to see it as a big load or a fault?
Contingency situation. What's a...
Could you read the question again?
In a contingency situation, what are the effects of the battery bank? Is the battery bank going to see it as a big load or a fault?
I'm not sure I understand the question.
Oh, yeah.
Okay, Georgia, you might need to rephrase or explain what you mean by contingency situation, and we'll get back to you on that one. And Lucas, an unexpected situation.
Oh, well,
Can you give an example, Georgia, of what you mean?
I mean, any interruption to the grid is, as standard, this battery will be connected behind a G59 and trip off.
Yeah.
They don't get any special treatment in that way.
Okay, hopefully that answers your question, Georgia, but if not, let me know. And Lucas from GTC has, he's asked about EFR and FFR. How can someone bid into the EFR or FFR given that solar has unpredictable outputs? The investor may breach its contract if the battery is not charged. What about high frequency response when the battery is fully charged?
This is the thing, is I've said, if you're doing any of these other scenarios, you can't be in FFR. You need your full capacity and your full ability to import and export to be able to be inside FFR. Realistically, so the base case was based on what other batteries are being installed to do. There isn't actually the base case for installing a battery on a solar park where it doesn't have access to its own export and import. It can only export when the solar park is not generating. And so I absolutely agree with you. So if you're using this battery for solar peak lopping, that's what the opportunity cost is. That is the cost of it not being in the main market where it could be generating money. So each of these use cases you compare to that cost, assuming you can get a contract, which is the much tougher thing now. And if the base case, whatever it is, arbitrage or FFR, everything, if the base case makes money, then asset operators won't be persuaded to bid into these other markets.
Okay, final question for this section from Neil Bailey. Would you recommend a different battery technology, such as flow batteries, for better access to the arbitrage opportunities, given that solar profiles are predictable against clients' load requirements?
I mean, you're sort of asking me a sort of investment level question there. I mean, technically speaking, flow batteries are great. They don't have the cycling issues of lithium, and they can cycle permanently. You can run them flat out, full to flat, as much as you want. They immediately sound like they're better for arbitrage, assuming you can use that extra depth to take advantage. Because of course, there is the slight thing that arbitrage is based on half-hourly prices. So if there's only 2 hours or an hour's worth of good arbitrage opportunity a day, then flow battery, you're not going to get the uplift from that. But I believe that flow batteries are likely to come forward more. I see lithium more as a power injection technology. So that's why it's being used for frequency response. It doesn't actually store that huge amount of energy, but it's able to absorb or insert it when it's needed. At the time when we looked at this, the cheapest technology was lithium, and we only wanted a 2-hour battery. The flow battery is a minimum of 5 hours. And they do have lower round-trip efficiencies, and round-trip efficiency was given weighting on this particular tender, and thus that round-trip efficiency loss does also reduce your income from arbitrage. I think flow batteries are a viable technology, depending on your use case. If you're using them to do peak lopping solar and it's to a client and it's a private wire, that's a totally different scenario to being open on the grid and doing solar peak lopping like that, because you're able to get a higher price per unit, and you've got a predictable price, and you can run calculations a lot more easily on the future revenues from that.
Excellent. Okay, right. Well, that was the last question that I've got on my list for now, so carry on.
Okay, we're near the end, I promise. We've got combining use cases. The combination method of resolve is a little bit naive in that it just adds together the individually calculated set points for the battery. And so we've ran across some limitations within this. For instance, ramp rate control and peak lopping at the same time you would expect to do, in that if the generation goes above a certain level, you would constrain it, and if it's below that level but spiking up and down, you would use ramp rate control to smooth it. However, we have a scenario where, for instance, the solar park is generating 800 kilowatts and we've constrained it to 500, but then the solar, so the battery is able to hold it at 500 kilowatts, but then the solar level drops and the ramp rate control goes, the solar level is dropping, I need to increase my export to offset that. Well, actually it doesn't, because the first use case, the peak lopping, is already holding it stable at 500. So until it drops below 500, the other use case shouldn't do anything. It would require significant reprogramming and a much more complex bit of kit to be able to understand the priority of these and the logic behind it. So I can understand why that wasn't working, but I will say that it is a much more complex control system that's needed for that. The base case is very important. I think that trying to put together an investable battery based off of, let's say, relying on 4 or 5 different use cases, some of which may change as the network demands change, I don't believe that investors will go for that. I think what you need is a base case that says this is the standard thing that the battery will be doing, but here's the additionality we can get by putting it here. We can get these contracts, or potentially get longer revenues if it's doing network support in an area that's expected to delay it for 5 or 10 years. That is of great interest to investors. Splitting capacity to do 2 things at once, in a way to sort of spread bets, hurts returns in a fiercely competitive business. So you pick the most lucrative use case and you do that. You don't try and do 3 at once with different parts of your battery capacity. There's slight variations on that. If you're doing the local support and you only have to offer a third of your battery to do that, then you leave the rest of your battery doing your base case. That's better, because you're getting more revenue from that third and then still getting your standard revenue from the other 2. But in terms of a sort of bet spreading type scenario, it's not right. And the only exception is the reactive power control mode with that non-linear trade-off. UKPM power potential is demonstrating multiple assets working with reactive power, and that's quite good. Each one sacrifices a little active power, or sometimes they don't sacrifice any. If they're generating at peak, they don't offer the reactive services, but at all the other times when they're not generating at peak, they're offering reactive power flow to the grid. DNOs are beginning their DSO transition. So this project has been able to see quite a few changes over the network and approaches to flexibility. Energy storage is still the sort of highest tier asset, the gold standard of what you can connect to the grid, because it can import, it can export, it has fast response time, but it can store energy for later. But it can be costlier than gas peaking plants and diesels to install, and it has twice the grid requirements. Instead of just generation, it needs demand as well. And batteries themselves then come under the P2/6 regulations of needing 2 routes to their demand, even though they might not need their demand because the generation hasn't been restored after a network problem. There is 3 gigawatts of project planning throughout the UK. Will they be built? Is a question with the big declines in frequency response contracts. Continuous regulatory change has reduced investor confidence, and there's a lot of changes ongoing, a lot of consultations, grid charges are being altered. This project has seen the rush and halt of the EFR and FFR, and now people are looking for other ways to make money with batteries. So the research has actually come out at a really good time, especially as DNOs are just beginning to start looking at these services. And DNOs can now get services at lower prices because the base case of FFR is lower. So DNO's got a better chance of competing, and batteries have a better chance of being involved because they're likely to charge less than the cost of reinforcement.
I would just add to that, though, the locations where those batteries are going to be installed, not typically where the DNO actually requires a service. They've gone for where they can get a good secure connection rather than where there is a constraint.
Yes, yeah, that's true. But looking forward, if there are longer contracts offered, and I think the key is the longer contracts offered, because frequency response was only we'll save that for the discussion slide. Network peak lopping can save everyone money. So DNOs don't have to pay out for the reinforcement. Energy storage developers can get longer contracts, and the consumer ends up getting charged less because they're not having to put miles and miles of very expensive, for instance, 132 kV cable and transformers in. If the DNOs offer long-term contracts, give projects confidence to go ahead, and we have this very huge report, and I think huge is the right word, report being published for learning and analysis so far, and there's data sets that will be able to be available to other people, so they can look at the operation of the battery and make their own learning and analysis. So this could just be the early conclusions from what we've done with the battery so far.
I received an update that report is on our website now.
It is on our website. Fantastic. Okay, and that is 110 pages approximately of reportly goodness.
Okay.
So on to our Q&A, I think.
Yes, so this is the final Q&A of the webinar. If anyone has any questions, either about what Christy and Jenny have just gone through now, or generally about the project, or anything that you would like to know, what the results of this project may go on to then have an effect on the industry, then please let us know. At the moment, I am looking at a blank sheet.
So I think, as well as pointing people towards the report that includes this analysis, I'd also point them towards, there's a separate report that covers the sale and relocation. That's been on the website for a few weeks now. That covers that in more detail.
Yeah. So if anyone wants to know D's experience of selling a second-hand battery, essentially, with utility scale battery, then all the information is in there.
UKPN are now selling theirs, incidentally. So we managed to get in there first as a feather in our cap, but they're now looking to sell their Leighton Buzzard one. Though I don't think they're going to move that one because
I think that would be a lot harder.
It's size of 4 tennis courts.
We will be sharing these slides afterwards with everyone who signed up to the webinar. And Gary has just said he's involved in selling that battery too.
Oh, right. Yes. Oh, Gary, yes. Yeah, I saw the announcement. Yeah.
I've had a question. Does this mean that collating battery with existing solar sites is financially unviable? Well, I think, Christy, you explained it's horses for courses.
It is. I mean, I struggle to see the investment case right now. I think that what we want is more variable pricing. If we could really push out solar, and I'll speak to my colleagues about getting some more solar parks installed, so that's on me. But if we put more solar out there, then the pricing in the middle of the day will decline further. If it, for instance, goes down to 0 or negative, then actually you start having that arbitrage opportunity becomes a lot bigger. At the moment, you can build solar. It's relatively cheap. The prices are declining all the time. You build solar, you sell it to the grid, you sort out a PPA quite often rather than taking the market price on the grid, and that's it. And adding what is quite an expensive asset to that, which then I don't feel is working flat out, because there's unpredictability of solar. At the moment, solar operators often don't predict the amount of generation that there's going to be, because there's no need. The power takeoff company does do that because they're trying to make the most money out of it. But as far as the park owner is concerned, the power flows out and they get paid. And if it comes in the afternoon or the morning or comes tomorrow rather than today, it doesn't matter. But if you put a battery there, you need predictability because you need it to be doing the absolute minimum time it can be on each thing to then bring in the revenue and move on to the next part.
I think one of the key learnings was that, you know, whilst all of the use cases worked very well technically, some of them didn't really have a very good financial use case, certainly in terms of smoothing the output from the solar farm. It worked like a dream, but you couldn't really think of how you'd actually get any money for that. And in terms of the other services, again, they work fine, but they are so location specific. You'd be very lucky to find a location where the DNO required support, but there was also a requirement for power factor correction for National Grid and reactive power services, and there also happened to be a local customer that you could provide a service for. So I think that locational element is a quite a high risk to an investment case. The only thing that sweetens that is the fact that we did find you could relocate a battery, you know, and get over that technical limitation. So if we envisage batteries being able to move around and make more use of locational issues, I think that does tip the balance a little bit in favour. But at the moment, the investment case really isn't there.
It's the only thing that springs to mind is if you're building a solar and a battery park together, they can not necessarily behind the meter, but share some of the assets, and that's a saving, and then split the grid cost between them, for instance.
So the inverters?
Just the cost of a DNO connection, substation, transformers, all the rest of that. They'd be able to connect to the same one and save money like that. But it's
and as well as not having certainty about what locational services are required, you then have the issue about those profiles, because it could be that you have multiple services to provide, but if those profiles actually clash, then you still can't provide those multiple services. That's why it's not as easy. You can't just generate an Excel spreadsheet where you put in the numbers and check boxes and it tells you whether or not there's an investment case there. It's still complex.
This is why specifically in the report I talk about how many hours you have to bid out to be able to provide this, and I always look for ways to reduce the amount of time and try and get more predictability. Is because if you say, well, actually we couldn't need it any time within 6 months, then you have to pay, if you want that contract, you have to pay 6 months of the standard batteries investment case of revenue. So if you take that as, even if we don't know what that is right now, if you take that as this has to be a percentage of IRR, then that you have to pay that much to get them not to, and possibly a bit more to cope with the admin cost of not just leaving the battery as it is and doing what it's doing.
Okay, so we're almost out of time. Do we
We've
need
got
to?
one last question,
Okay.
Which I think is actually a really good one, and I'm surprised somebody hasn't picked it up. So obviously this project is all focused on solar and storage. So would that change? Would the usage case change and the business case change if we were looking at wind energy or other form of energy generation?
I would say my personal view is that wind is even worse to try and connect the battery to do multiple things. Because at least with solar, you can say overnight the battery can do what it likes. Whereas you have the advantage of more predictability with wind, so there is that. But the markets at the moment are monthly, for instance for FFR, and wind could then be needing you to peak lop at any time. And so I think that the solar has the advantage of at least 50% of the time you're not going to need it for any solar related stuff, and you can do other things. That's my gut instinct on it.
Yeah, certainly make your control algorithm and your scheduling much more complicated, because whilst you're quite right, you'd have the benefit of having it's easier to forecast the wind output from the forecast weather data that you have than it is for the solar. But then you have to be much more clever in the way that you actually slot the different blocks of services together.
Yeah. Okay, and we've now reached 12 o'clock, and yes, Philip, we will send out a link to the reports when we're sharing the slides as well.
Yeah.
Okay. All right. Well, thank you very much for watching.
Thanks for attendance and for your questions.
Yeah. And I'll just pop the final slide up, which is there. And
Nothing else. Yes,
Nothing else to add,
we'll get
yeah.
back to you with the links to the slides.
Lots of thanks.
Okay, thank you very much.
Thank
Cheers,
you.
everyone.
Bye.